Chapter 3 deals with stoichiometry, and we're going to start looking at atomic isotopes first of all. Atomic isotopes are determined, as it says, by using mass spectrometry, and this diagram shows us a schematic for a mass spectrometer. Samples are injected as a gas, and they enter at one end of the mass spectrometer. They travel through a series of plates through an electric current. They're accelerated so that they're moving close to the speed of light. They are ionized, so they're either positive or negative ions. They then pass through a magnetic field. Because they're ions, the magnetic field is going to bend the path of these particles. And the path will bend, and they're aiming for a detector plate, but it's bent so that we can take advantage of gravity. The heavier particles are going to land lower down on the detection plate. The lighter particles are going to land higher up on the detection plate, so we can get a sense of how many particles with each mass land at which target site. And that gives us a percentage of each particle's presence. Average atomic mass that we see on the periodic table is a weighted average of all the isotopes based on the percent abundance of each of the isotopes as found in nature. If we look at carbon, carbon-12 has been assigned the exact mass of 12.0000. It's defined that way. Carbon-13 has a mass of 13.0034, and that is determined by the masses of protons, neutrons, and electrons as defined by carbon-12. The isotope carbon-14 is essentially negligible in nature, so it really contributes next to nothing for the average atomic mass for carbon. Periodic table gives us the weighted average of each element, and to find the average, what we're going to do is we're going to take the percent abundance of each isotope and multiply it by the atomic mass of that abundance. Moles is a unit of counting numbers. It's a number of particles. And AMU's units are units referring to atomic quantities. Atomic mass unit is the mass of an atom or a molecule. And it's really impossible to measure anything that's that small, so we tend to convert our measuring units to some sort of corresponding value that is measurable, namely grams. Avogadro, our friend from last chapter, worked with gases, and what he found was that if he kept temperature constant, if he kept pressure constant, the volume of the gas depended on the number of particles in his container. And doing a vast number of experiments, what he found is essentially to three significant figures: 6.02 times 10 to the 23rd particles of any substance will give you a mole of that substance. And a mole, again, is a counting quantity similar to counting quantities such as a pair, a dozen, or a gross. A mole is a counting quantity. If I were to measure out 1 mole of any substance, it is equivalent to the formula mass of that substance in grams. For example, if we are to look at water, water's 2 hydrogens plus 1 oxygen. If I add the average atomic mass of those 3 atoms together, I get 18.02 grams is the mass of 1 mole of water. Molecular mass for covalent compounds is equal to formula mass for any kind of compound. Molecular mass is another synonym. Percent composition, we're looking at a compound formula and we're determining percent by mass of any element in the compound. First thing we're going to do is we need the compound formula. Second thing we're going to do is we're going to take the average atomic mass of each element and add them together. If I have more than 1 copy of a particular atom, then I'm going to multiply its atomic mass by the number of copies I need. So I have 1 copy of sodium, 1 copy of hydrogen, 1 copy of carbon, but I need 3 copies of oxygen, so I'm going to multiply that 16 by 3. When I add them all up, I get the formula mass for sodium bicarbonate, and that's 84.01 grams per mole. If I wanted to find the percent of sodium in sodium bicarbonate, I'm going to take the mass of sodium and divide by the mass of the compound. So 22.99 grams divided by 84.01 grams gives me a decimal number. If I convert that decimal into percent, 0.2737 gives me 27.37, should be a 37%. Sodium I want to define the percent of oxygen in the same compound. I'm going to take the mass of all the oxygen, which is 3 times 16, and I'm going to divide by the mass, the formula mass of the entire compound. If I do this, I'll get the percent of oxygen in my compound is 57.14%. Empirical formulas. Once we figured out the percent of each element in a compound, and we can do that using a chromatograph or a mass spectrometer, as we talked about earlier, I'm going to take the percentage of each substance, and I'm going to make the assumption that I have 100-gram sample, and what that allows me to do is the percentage of each element then can be converted into grams. So if I have 26.58% of potassium in my compound, then that's the same as saying in 100 grams of my sample, 26.58 grams of it is potassium. So when I'm doing empirical formulas to look at the mole ratio of elements in a compound, and I start with percent composition, I'm going to convert those percentages to grams. If I'm already at grams, I don't have to do this step. What I need to do now is find the moles of each element. So I'm going to divide the grams of each element by its average atomic mass, and that will give me the number of moles of that element in the compound. So for potassium, I've got 0.6798 moles. For chromium, I have the same number of moles. For oxygen, I have 2.379 moles. Once I have the number of moles of each element present in the compound, I'm going to divide each of those mole values by the smallest mole quantity. So 0.6798 is the smallest of the 3 mole quantities. 2 of them have the same mole value. So I'm going to get a mole ratio now. My mole ratio is 1 to 1 to 3.5. What I need to do now is get that into a whole number ratio. So if I take each number and multiply it by 2, I'll get a whole number ratio because I need whole numbers in my moles. If at this point I still have fractions, I'm going to round, and I'm going to round down if it's less than 0.2. I'm going to round up if it's greater than 0.8. And then these numbers become my formula subscripts. So my compound is potassium dichromate K2 Cr2O7. And that's using percent composition to find empirical formula.